Today, we are mastering the fundamental methods of proof required for the IB Mathematics Analysis and Approaches higher-level syllabus. Specifically, we will cover mathematical induction, proof by contradiction, and the use of counterexamples. These concepts are vital because they form the logical backbone of pure mathematics. In your IB examinations, proof questions often appear in Paper 1 or Paper 3, where rigorous communication is just as important as the final result. By the end of this lesson, you will be able to construct formal arguments that satisfy the strictest mark schemes. We begin with mathematical induction. This is a powerful technique used to prove that a statement, which we call P of n, is true for all natural numbers n. Think of it like a line of falling dominoes. To ensure every domino falls, you only need to guarantee two things. First, you must knock down the first domino. Second, you must ensure that if any one domino falls, it will inevitably knock down the next one in line. In mathematical terms, this translates to the basis step and the inductive step. First, the basis step. We show the statement holds for the smallest value, usually n equals 1. Next, the inductive step. We assume the statement is true for an arbitrary integer k, and using that assumption, we prove it must also be true for k plus 1. Finally, we state the conclusion. This formal summary is essential for gaining full marks in the IB. Let's apply this to a series. We want to prove that the sum of the first n integers, written as the sum from r equals 1 to n, of r is equal to n times n plus 1, all over 2. We start with the basis step for n equals 1. The left-hand side is simply the first term, which is 1. The right-hand side is 1 times 2 divided by 2, which is also 1. Since both sides match, the basis step is complete. Now for the inductive step. We assume the statement is true for n equals k. This is our inductive hypothesis. We must now show it holds for n equals k plus 1. We split the sum into the first k terms plus the k plus 1 term. Using our hypothesis, we replace the sum of k terms. Now, we factor out k plus 1. This simplifies to k plus 1 times k plus 2 over 2, which matches our goal. We finish with the formal conclusion to secure that final communication mark. Next, we examine proof by contradiction. This is an indirect method of proof, where we demonstrate that a statement must be true, because its opposite leads to a logical impossibility. The intuition here is simple. In a logical system, if a premise leads to a broken result, like saying a number is both even and odd, then the premise itself must be false. In the IB, this is often used for proving numbers are irrational, or that there are infinitely many primes. Let's prove that the square root of 3 is irrational. We assume the negation. Suppose the square root of 3 is rational. If it is rational, it can be written as a fraction a over b in its simplest form. This means a and b share no common factors. Squaring both sides shows that a squared is a multiple of 3. Because 3 is a prime number, this implies that a itself must be a multiple of 3. Substituting this back in, we see that b squared is also a multiple of 3, which means b must be a multiple of 3. If both a and b are multiples of 3, they share a common factor of 3. This directly contradicts our initial assumption that the fraction was in simplest form. The assumption failed, so the original statement must be true. Therefore, the square root of 3 is irrational. Now, let's look at the most efficient way to disprove a statement, the counterexample. In mathematics, a universal statement claims that something is true for every single element in a set. To prove such a statement is false, you do not need a complex derivation. You only need to find one single case where the statement does not hold. Think of it like the statement, all swans are white. You don't need to look at every swan in the world to prove this is wrong. You only need to find one black swan. Consider the claim that the expression n squared plus 41n plus 41 always produces a prime number for any natural number n. To test this, let's try a clever value for n. If we let n equal 41, the equation becomes p of 41 equals 41 squared plus 41 times 41 plus 41. Simplifying this, we get 41 squared plus 41 squared plus 41. Factoring out 41 gives us 41 times the sum of 41, 41, and 1, which equals 41 times 83. Because the result is a product of 41 and 83, it is a composite number, not prime. Therefore, the universal claim is false. Let's look at a geometric example. There are no positive integer solutions to the equation x squared plus y squared equals 10. If we look at the circle representing this equation, we can see it passes through the point 1, 3. 1 squared plus 3 squared equals 1 plus 9, which equals 10. Since 1 and 3 are both positive integers, this single pair acts as a counterexample that disproves the statement entirely. Let's tackle an authentic IB-style question that combines these concepts. The question has two parts. Part A, use mathematical induction to prove that 4 to the n plus 15n minus 1 is divisible by 9 for all positive integers n. Part B, hence, or otherwise prove that 4 to the n plus 15n minus 1 can never be prime for n greater than 1. For Part A, we follow our structured steps. We start with the basis step where n equals 1. Plugging in 1, we get 4 to the power of 1 plus 15 times 1 minus 1, which equals 18. Since 18 is 9 times 2, p of 1 is true. Next, the inductive step. We assume p of k is true. This means we assume 4 to the k plus 15k minus 1 equals 9 million for some integer m. We must show the expression holds for k plus 1. Let's expand the expression for k plus 1. We get 4 times 4 to the k plus 15k plus 14. To use our inductive hypothesis, we replace 4 to the k with 9 million minus 15k plus 1. Expanding the bracket gives 36 million minus 60k plus 4 plus 15k plus 14. Simplifying terms yields 36 million minus 45k plus 18. Finally, we factor out the 9 to get 9 times the quantity 4 million minus 5k plus 2. This is clearly a multiple of 9, completing the inductive step. For Part B, since we proved the expression is always divisible by 9, then for n greater than 1, the value will always be a multiple of 9 greater than 9. Consider a proof by contradiction. If it were prime and a multiple of 9, it must be 9 itself. But 9 is not prime as it is 3 times 3. Therefore, it can never be prime. This is a concise proof by contradiction relying on our induction result. To secure a grade 7, you must avoid these 3 frequent pitfalls. First, students often lose the final mark in induction by not writing a complete conclusion. You must explicitly state that because the basis step is true and the inductive step holds, the statement is true for all natural numbers by the principle of mathematical induction. Simply writing "therefore true" is not enough. Second, when proving irrationality, many forget to state that the initial fraction a over b is in its simplest form, where the greatest common divisor is 1. Without this, you have no logical contradiction to reach at the end. Third, when using a counterexample, students sometimes provide an example that doesn't actually fit the domain of the question. If a statement says, "For all real numbers," you can use a fraction or negative number. But if it says, "For all integers," your counterexample must be an integer. Now for some high-level strategy. In induction, always keep your target expression for k plus 1 clearly visible on the side of your page. This helps you figure out how to factorize your algebra toward that specific goal. Regarding marks, remember that IB examiners award method marks. Even if your algebra gets messy in the middle of an induction proof, as long as you have a clear basis step, a clear assumption, and a clear attempt to use that assumption, you will still collect the majority of the marks. Never leave a proof question blank. Finally, for contradiction, always start by explicitly writing "assume the negation is true." This tells the examiner exactly which logical path you are taking. It is time to test your understanding. Please pause the video and attempt these 3 questions before we go through the solutions. Take a moment now to work through these carefully. Let us review the solutions. For the easy question, we need a counterexample for n squared plus n plus 1. If you chose n equals 4, you found that the result is 21, which is composite. Therefore, the statement is false. For the medium question, we use contradiction. Assume n is odd. Squaring an odd number always results in another odd number. This contradicts the given information that n squared is even. So n must be even. For the hard question, our basis step starts at n equals 4. In the inductive step, we use the property that k plus 1 is definitely greater than 2 to complete the inequality. To conclude, here are the essential points from today's lesson on proof. First, remember that mathematical induction is like a chain reaction. You must prove the first case and then prove that each case guarantees the next. Never omit the formal concluding statement, as it is a specific requirement in the IB mark scheme. Second, for proof by contradiction, clarity is key. State your initial false assumption clearly and look for a violation of a known mathematical rule, such as a fraction that cannot be simplified further or a number being both even and odd. Third, use counterexamples as your primary tool for disproof. You don't need to show why a statement is generally wrong. You only need one specific instance where it fails to hold true. Finally, focus on your mathematical communication. Use correct notation for sets and clear logical connectors. In the higher-level syllabus, the way you present your argument is just as important as the logic itself.